Hi everyone, welcome to Lab Exercise 4.1 where we will be discussing population genetics. The first thing that we're going to do is analyze a hypothetical population using the Hardy-Weinberg principle. The Hardy-Weinberg principle states that if there are no interfering factors, such as a natural disaster or a small population size or other things that could affect the population frequencies, that we should expect the populations to remain relatively constant. Meaning if I showed up and looked in the forest and found a population of snakes that 70% of them were red, then I can expect to come back in 5 years and count those snakes, and I should reliably be able to predict that 70% of them are going to be red. Now, whether or not that actually happens is going to be in the next step, but first we're just going to analyze that ideal proportion. So, Hardy-Weinberg decided that he needed a way to measure 100% of the population. So we want to find out what 100% of the population is. If I'm going to measure 100% of the population, I'm going to measure all of the individuals that are homozygous dominant. And then I'm going to add to that all of the individuals that are heterozygous. And then I'm going to add all of the individuals that are homozygous recessive. Now, if I'm going to do that, I can't use these symbols because remember from last semester, we're very inconsistent. If I'm talking about yellow, I'll use a Y. If I'm talking about kangaroos, I might use a K. It's very random. So Hardy-Weinberg decided that instead of saying the dominant allele, he's going to use the letter P. And since this individual has 2 dominant alleles, they're going to get 2 P's, and we're multiplying those. Then we need to find out the value for the heterozygotes. They have 1 dominant allele and 1 recessive allele. Hardy-Weinberg decided we're going to use the letter Q. Then we are going to find the individuals that are recessive. If they have 2 recessive alleles, they're going to get 2 Q's. Now, when we do a Punnett square, such as the one below, we end up with actually 2 boxes of heterozygotes because we crossed 2 parents. So we have 2 copies of the heterozygotes. So instead of actually saying PQ, we have to multiply that by 2 in order to count all of the individuals. To simplify this, P times P is the same as P squared. We're just going to add the 2PQ. Then we're going to add the Q times Q, which is Q squared. And if I were to write 100% of the population as a proportion, we could just say 1, because 1 is the same as saying 100%. Now, what if I only wanted to find the number of alleles, not the number of individuals? So this would be the frequency of individuals that have 2 dominant alleles. What if I wanted to look at the entire population and only count the dominant alleles? I don't care whether they're heterozygous or homozygous. In that case, I'm going to split this down the middle, and I'm going to send half of it to this category and half of it to this category. Well, we already said that the dominant allele is called P, so all 3 of these would be P, and all 3 of these together would be Q. So we get a second formula that says all of the P's together plus all of the Q's together should also equal to 1 because it's also the whole population. So we're going to be using both of these equations depending on our needs. Let's look at the first problem. The first problem says that this population, we have attached earlobes and we have free earlobes. Now, if I have attached earlobes, it says it's 2 recessive genes. So attached, I'm going to say, is little a, little a. Then it says free earlobes, you have to inherit at least 1 dominant allele. So for free earlobes, it can be dominant A and then it doesn't really matter what's next. It could be a dominant A or it could be a lowercase a, but at least one dominant allele. Then it gives us this last bit of information. It says the frequency of the recessive allele is 70. When I'm talking about the frequency of the allele, I'm not talking about an individual that is homozygous or homozygous recessive. I just want the frequency of the allele. So we're talking about P or Q. In this case, the recessive allele is Q. So over here, they have given us Q. I'm going to write it out to the side. Q is equal to 70%. If we write that as a proportion, it's 0.7. Now, I can easily find P because I know that P plus Q is equal to 1. If P plus 0.7 is equal to 1, all I'm going to do is subtract 0.7 from both sides. That cancels out, and I end up with 1 minus 0.7 is equal to P, or P is equal to 0.3. We can double check our answers because they should add up to equal 1, which they do. If I add these together, it equals 1. Now, it's wanting to know some different information. We found P and we know Q. Now it's asking us for homozygous dominant. If I'm looking for homozygous dominant, I'm looking for all of the individuals that have that genotype. Well, if we look at our Hardy-Weinberg equation, if we're looking at homozygous dominant, we're looking at P squared. So what I'm actually looking for is P squared. Do I know P? Yes, I do. It's 0.3. So all we have to write is 0.3 squared, and we should get the frequency of all of the individuals that would have this genotype. If I multiply this out, I get 0.09, or 9% of the population should be homozygous dominant. Now it wants to know about heterozygous. I'm looking for heterozygous. If I go over here and look at my Hardy-Weinberg equation, heterozygous individuals, I'm looking for 2PQ. All right, 2 times P times Q, and I know both P and Q, so I can just multiply that out. 0.3 times 0.7. If I multiply these together, I'm going to get 0.42, or 42% of the population is heterozygous. Sorry, that cut off in the video. Last, we're looking for homozygous recessive. If I look at my Hardy-Weinberg equation, homozygous recessive is Q squared. So I am looking for Q squared. I know Q already is 0.7, so we just need to square it. 0.7 times 0.7 is 0.49, or 49% is homozygous recessive. I can double check my answers by adding these three numbers together, which should equal to 1. In the last step, it's not asking me the frequency, which should be a percent. It's asking me for the actual number of people in the population that would have those traits if the entire population was 7,000. So I just have to come up with a formula for a population of 7,000. If I'm looking for free earlobes, I can come up here and look at my notes. Free earlobes have to at least have one dominant allele. Doesn't matter what the second one is. So if I'm looking for a population of 7,000, how many individuals have free earlobes? I'm going to multiply that against the frequency of free earlobes. Here, the frequency is 0.09 for homozygous dominant. That is not all of the individuals that have free earlobes, though. Heterozygous also has free earlobes. So we're going to multiply this by 0.42. This should equal, if we multiply this out, the number of individuals that have free earlobes, which is 3,500 and 70. Now I'm looking for attached earlobes. If I look at my notes, attached earlobes is only homozygous recessive. So I'm going to take our total population, which is 7,000 people, and multiply it by the frequency of homozygous recessive, which is 0.49. I apologize, we add these together. We don't multiply them out. That's the correct answer. Okay, so 7,000 times 0.49, if we plug that into the calculator, is 3,430. All right, let's do another practice problem. The next practice problem says that 18 out of 50 lizards have short tails. Short tails is a recessive trait, so I'm already thinking that this is going to be homozygous recessive. If they are telling us the frequency of homozygous recessive, I'm looking over here, this is the frequency of homozygous recessive. They have just told me that Q squared is equal to 18 out of 50. According to this problem, 18 out of 50 lizards have this recessive trait. So Q squared must equal 18 out of 50. If I multiply that out, Q squared is equal to 0.36. Now, I don't need to know Q squared as Q squared as much as I need to know Q. So if I want to know what Q by itself is, all I need to do is square root it. But I can't just square root one side, I'm going to square root both sides. So Q is equal to 0.6. This is my Q value. Now that I know my Q value, my P value is very easy to calculate because 1 minus Q should equal P. So my P value is 0.4. Now I have these two values, I can calculate anything it's asking me. All right, it says calculate the frequency of the recessive allele. If I'm looking for just the recessive allele, I'm looking for Q. And next it says calculate the frequency of the dominant allele. If I'm looking for the dominant allele, I'm just looking for P. I've already calculated those. Q is equal to 0.6, P is equal to 0.4. Last, it says calculate the frequency of heterozygous individuals within the population. The population, if we look here, is 50, and we're looking for heterozygous individuals. Heterozygous means that we're looking for 2PQ. So what do? We make a formula. The total population times the frequency, 2PQ. All I have to do is plug in my numbers. 50 times 2 times 0.6 times 0.4. And this is equal to 50 times 0.48, which is equal to 24 heterozygous individuals. So if I'm going to write that out. So 24 individuals would be heterozygous. We have one more practice problem. In this practice problem, we have sheep with white wool, which is dominant. So let's say big W, or big W, little w. Then we have black wool. Black wool would be recessive, so little w. Now it says 25% of the sheep are black. that means that little w, or as we like to call it, Q squared, is equal to 25%. We don't like to work with percentages though, so 0.25 is our answer. So Q squared is equal to 0.25 based on the information in this practice problem. It first wants us to calculate the frequency of true breeding white sheep. Remember, true breeding are homozygous. So I'm looking for just homozygous dominant. If I'm looking for just the frequency of homozygous dominant, I'm looking for P squared. I'm not ready to plug in yet though, because I don't quite know what P is. Next, it's asking for the frequency of hybrid sheep with white coats. So big W, little w. That means we're looking for 2PQ. Again, I'm not quite ready to plug in because I don't know P and I don't know Q. So let's stop there and find P and Q so we can move forward. If we know Q squared is equal to 0.25, in order to find Q, all I have to do is square root both sides. So Q is equal to 0.5. This seems like kind of a big number, but it ends up working out because 1 minus 0.5, P must also equal 0.5. So let's plug in our numbers. 0.5 squared is the same as 0.25. So we had 25% black sheep. We also have 25% true breeding white sheep. Next, we want to know 2PQ, so 2 times 0.5 times 0.5 is equal to 0.5. All right, so half of our sheep are going to be heterozygous white. That means 75% of our sheep are white. Now, it's wanting to know the number of black sheep. We would expect if the population was 750. So let's multiply our proportions or our frequencies by our population, 750. If we're looking for black sheep, it's going to be 750 times the Q squared number, okay, which is 750 times 0.25, which is 187.5. You cannot really have half of a sheep though, so we're going to call that about 188. On the quiz, it probably has the decimal, but in reality, we can't have half of a sheep, so we're going to say 188. Now, the next one is wanting to know the number of white sheep. Remember, I can't just do white. I can't just do one of the two categories because both of these are white. We said both both dominant homozygous and dominant heterozygous both express white. So I'm going to take my population and I'm going to multiply it not just by P squared. I'm also going to add 2PQ. Plug those numbers in, I end up with 750 times 0.75, which ends up 562.5. Again, we really don't like half sheeps, so we're going to round that to 563. Oh, this is black sheep. And this is white sheep. All right, next is our corn genetics. The first thing that we're going to do is identify our categories of corn. We have a little key here and it says, it's hard to see on the video, but in person it's A, B, C, and D. What we have is a purple round kernel a yellow round kernel, a purple wrinkly kernel, and a yellow wrinkly kernel. And we're going to be counting those on one of these ears of corn. So we see how some of them are round in yellow, this really bright yellow color. Some of them are wrinkly in yellow. Some of them are round and purple, and some of them are wrinkly and purple, like over here. There's 2 of them right there. We're going to count all of these. First, before we start counting, we need to find our ideal expected values. In order to find our expected values, we're going to do a dihybrid cross. Imagine that the parents are both heterozygous for color and shape. So we have 2 purple smooth parents, and we're going to find out the expected value of all of the offspring. Remember, in order to do a dihybrid cross, we need to use FOIL, the FOIL method. So I'm going to put one parent at the top, big P, big S, little s, and one off to the side, big P, big S, little s. And then I'm going to use FOIL. This F in FOIL stands for first. So I'm going to use the first P, big P, and the first S, big S. O stands for outer, which means I'm going to take the first P and the last S. I stands for inner. I'm going to take the second P and the first S. And L stands for last. I'm going to take the small p and the small s. We should get the same exact thing on the left column if the parent is the same, which in this case is. The parent could be different. You would have to do FOIL over again, but our prediction is that they're the same. So I'm going to put the same information. And then I'm going to do the cross where I pull this down and pull this across. In this first one, I should get big P, big S, little s. Likewise, if I do it to the whole thing and I pull this down and pull this across, I will end up with little p, little s, little s. We need to fill this entire chart by pulling down and then pulling across. All right, and we would continue that pattern. Okay, next we need to identify the phenotype. So I have some that are going to be purple, some that are going to be yellow, some that are going to be wrinkled, and some that are going to be smooth. So let's start looking at color. If it has a capital P at all, it will be purple. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 purple P's. Out of those 12, 9 of them also have a capital S. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 that are purple and smooth. It has to meet both requirements. The rest of the 12 is going to be purple and shrunken. Now I need to find my yellows. If it does not have a capital P, it is a yellow. So I have these 4 yellows right here. 3 of those yellows have a capital S, so they're yellow and smooth, but only 1 is neither purple nor smooth. It is yellow and shrunken. So we only have 1 here. And these are our expected values. They're all out of 16. So this would be 9 divided by 16, 3 divided by 16, and 1 divided by 16. This is our frequency of this phenotype. Let's go to the next page. On the next page, we have this chart, and it is asking us the genotype of each of these categories. So as we look at our old page, we know that purple and smooth has to have at least 1 capital of each. So my genotype at least has 1 capital P and 1 capital S. We don't know what that second one is. Next, purple, we know that it has to have at least 1 capital P, but it's shrunken, so it for sure has to have 2 lowercase s's. Yellow and smooth, if it's yellow, it's going to have 2 recessive alleles, so both of these have 2 recessive alleles, but smooth has to have at least 1 capital, shrunken is 2 small ones. Now we're going to count our corn. We're going to count individually. If you are in face-to-face, I provided these little pointers. Anything to keep you on track and make sure that we're counting properly. I find it best to go row by row and record all of one phenotype and then switch to the next phenotype. Now, the instructions say that you only have to count 5 rows of corn. I did not read that part, so I counted a whole bunch of corn, the whole corn. But what we would do is we would say, I'm looking for purple and smooth, so I'm just going to count all of the purple and smooth down 1 row. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So in this row, I had 18 purple and smooth. Now I can go in the same row and count purple and wrinkled. 1, 2, 3, 4, 5, 6, 7. 7 purple and wrinkly. Then I'm going to go to yellow and smooth. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 yellow and smooth. Now yellow and shrunken. 1, 2, 3, 4. So only 4. Make sure to record your answers and stay organized. What I ended up getting when I counted my corn, which I said I overcounted, I got 300, let me look at my notes, 312, and then 114, 95, and then 44. Why my pencil keeps... Now that we know our observed for each of these 4 categories, we're going to add them all together, plug this into your calculator, and we get 565 for our total population. Our total population is 565. Now we're ready to move to question number 3. Question number 3, we need to fill out these 3 columns and then find our total chi value. So our expected number, on a previous page, we figured out the expected value for each of these categories, which was 9/16, 3/16, 3/16, and 1/16. So that's the expected frequency. If we want to know the expected number, we're going to have to multiply this by the total population, which we know is 565. So we just replace that number with 565 and then plug that into your calculator. Okay, so 565 times 9/16 is 317.8. And if we continue down, plug all of these numbers into your calculator, we get 105.9, we get 105.9, and we get 35.3. Now this is the number that I would expect to get if we followed the ideal values of 9/16, 3/16, 3/16, and 1/16. So let's see if our observed or our actual number counted matches. We're just going to pull these numbers down here: 312, 114, 95, and 44. Notice that these numbers are pretty similar. There's a little bit of deviation, but pretty similar. The last column, we're just going to plug in this formula: observed minus expected squared divided by expected. So for this first one, I'm going to take the observed, 312, and I'm going to subtract the expected, 317.8. This whole thing needs to be squared, and then that whole thing needs to be divided by the expected, 317.8. If I plug all of that into my calculator, I get 0.106. This is my chi value for just purple and smooth. I need to find the chi value for each category. So again, plug those numbers into this formula and plug that into your calculator. We should get 0.620, 1.122, and 2.144. Notice that a larger number indicates a larger deviation from expected value. But we are not done yet. We now have to find the entire chi value, which means I'm going to add together all of these values. If I add them together, plug that into your calculator, we get 3.99. This is our chi value that we're going to compare to our critical value. Let's find the critical value. The only way to find the critical value is to use a critical value chart or a chi-squared chart. The first thing we need to know is degrees of freedom. If you remember, degrees of freedom is equal to the number of categories minus 1. If we look on the previous page, we have 1, 2, 3, 4 categories. So our degrees of freedom is 4 minus 1, or 3 degrees of freedom. So I'm only going to be looking at this row right here. Next, I need to find my probability, and for our purposes, probability is always 5%. That just is telling us how specific do we want our answer, and we want our answer to be within 5% of the tail. So we're looking at the 5% column. If we go all the way down the 5% column and all the way across the degrees of freedom column, we end up with our critical value, which is 7.82. So 3.99 is less than 7.82, our critical value. That means this falls within the good fit value. So we are a good fit. What does that mean? Well, if we have a normal population, a normal curve, about 5% of the population up here would be considered an outlier, an extreme. That's where that p-value comes from. And this number right here that separates a good fit from a poor fit is the crit value. So for our purposes, it's 7.82. If our chi value is 3.99, it might fall somewhere over here, and this is within the normal range. So this is not statistically significant. And that means that yes, we do think that these were the actual parents. The last thing that we need to do is the genetic survey. You can scan this QR code or type in this web address, and we will come to an observable human traits survey. We're going to fill out our own traits. So whatever traits you have on your body, that's what you're going to do. I actually have detached earlobes, not attached earlobes. Next, I can roll my tongue. If you cannot roll your tongue, you would choose this one. I have dimples. If you have dimples, you're going to select this one. If you don't have dimples, you'll select this one. I am right-handed. If you are left-handed, you'll select this one. I do not have a widow's peak. I have a straight hairline. At least I think. I'll have to double check that, guys. But if you have a straight hairline, you'll select this one. If you have a widow's peak, you'll select this one. Last is a hitchhiker's thumb. That just means that you can hyper flex your thumb. Some people can hyper flex both thumbs. Some people can only hyper flex one thumb. If you can hyper flex at least one thumb, you are positive for hitchhiker's thumb, like myself. If you really can't bend your thumb that much, then you have a straight thumb. The last one is the PTC paper. You will not be able to do this from home, but in class we have a small strip of blue paper, and if you place that on your tongue, you may be sensitive to that taste, which is a very bitter taste. Most people in our class, however, do not taste the paper and are not bothered by the PTC. PTC is a chemical that makes a bitter taste, and it is found a lot in like broccoli or Brussels sprouts. So if you just absolutely hate Brussels sprouts, it may be your genetics. You may genetically be more sensitive to that flavor than someone else. After you click this, we are going to submit and see previous responses. When we see the previous responses, we're going to be able to see everyone's answers for the entire class. So for earlobes, most people, 75%, have detached earlobes. For the next trait, most people can roll their tongue, and this is just people in our class. It may or may not be representative of the entire population. About 50% of the class has dimples and 50% does not. Most of the class is right-handed, 95.9%, almost 96% of our class is right-handed. And then most of our class actually has the recessive straight hairline, and only about 25% have the widow's peak, which is a dominant trait. Then we have 71% have a straight thumb, so those who can hyperfixate their thumb or hyperflex their thumb are in the minority. And the last one is PTC. Most people in our class cannot taste the PTC. Those of Eastern European descent are much more likely to be able to taste it. So the majority of our class cannot. Thank you for joining me this week. If you want to fill those numbers out so you have them for your quiz, I look forward to seeing you for next week in 4.2. Have a great weekend.